Hi learners, welcome to the course Quantum Chemistry. In this module, we are discussing one-dimensional harmonic oscillator. This module contains one-D harmonic oscillator description, Schrodinger wave equation for one-D harmonic oscillator, solutions of Schrodinger wave equation, recursion relation, Hermite polynomials, wave functions and energies of 1D simple harmonic oscillator, and graphical representation of energy as well as wave function. First of all, one-dimensional harmonic oscillator. A brief description is here. A diatomic molecule is the quantum mechanical analog of classical version of harmonic oscillator. This represents a harmonic motion. A simple harmonic oscillator is an oscillator that is neither driven or damped. Simple harmonic oscillator represents the vibrational motion and is one of the few quantum mechanical systems for which an exact solution is available. That means simple harmonic oscillator is a quantum mechanical system which is exactly solvable. Or only SHO is an exactly solvable system, just like the hydrogen atom problem, particle in a ring, rigid rotator, particle in only box, etc. Now, Hooke's law. According to Hooke's law, the force acting on the molecule is given by F is equal to minus Kx, where x is the displacement of the oscillator from the equilibrium position and K is a constant known as the force constant. A molecule which can be considered as an oscillator also obey this Hooke's law. F is equal to minus Kx. The Hooke's law potential energy, that is Vx, of a molecule that acts as a simple harmonic oscillator is given by the relation Vx is equal to minus integral 0 to x f of x. That is, we can replace f with minus Kx and substitute for f to get the relation integral 0 to x kx dx. And we know integral 0 to x kx dx equal to k into integral 0 to x x dx, that is equal to k into x square by 2 or simply half kx square. So, the potential energy Vx of the system as per the Hooke's law is equal to half kx square. This we derived from Hooke's law. Thus, a simple harmonic oscillator, that is a diatomic molecule which can be considered as a simple harmonic oscillator, has potential energy Vx equal to half kx square if it execute only harmonic motion. Now, the plot of potential energy. We have the Hooke's law potential energy Vx is equal to half kx square. It should be noted that this expression, that is half kx square, depicts the mathematical expression of a parabola. Hence, if we are plotting Vx, we will get a parabolic shaped curve. The plot of potential energy of the system as a function of the displacement. The left hand side is potential energy and the right hand side consists of the variable that is displacement. So, if we are plotting potential energy as a function of displacement, that is we are taking potential energy along the y direction and displacement x along the x direction, we are getting a parabolic shaped curve or a parabola. This is the Hooke's law potential energy of a simple harmonic oscillator that execute only simple harmonic motion. Now, vibrational frequency of simple harmonic oscillator. The vibrational frequency of a simple harmonic oscillator of mass m is given by the relation vibrational frequency nu is equal to 1 by 2 pi into under root k by m. Since in the present system we are dealing with the molecules that consist of atoms. If we are having a diatomic oscillator or a diatomic molecule, it is having two atoms. The mass of the first atom is m1 and the mass of the second atom is m2. Then we can take the mass of the molecule as a reduced mass. Reduced mass mu is given by the expression m1 m2 divided by m1 plus m2. m1 plus m2. Therefore, this vibrational frequency can be more conveniently represented in terms of the reduced mass of the system. That is, this m can be replaced by reduced mass mu. So, for a diatomic molecule or a molecule that executes a simple harmonic motion, the vibrational frequency is given by the corrected expression nu is equal to 1 by 2 pi into k by mu the whole raised to 1 by 2. That is 1 by 2 pi into under root k by mu, and mu stands for reduced mass of the diatomic molecule or the molecule under consideration. Now, the Schrodinger wave equation for one-dimensional harmonic oscillator. As in the case of every exactly solvable system, the first part is the application or the incorporation of Schrodinger equation into the present system. And the Schrodinger wave equation for a simple harmonic oscillator that execute one-dimensional simple harmonic motion is given by minus s cross square by 2m d square by dx square plus half kx square into psi x is equal to energy into psi x. This is derived from the original equation, that is Hamiltonian psi is equal to energy into psi. For one-dimensional motion, the Hamiltonian reduced into minus s cross square by 2m d square by dx square plus v. V represents the potential energy. On operating this operator into psi, we are getting this expression, that is minus s cross square by 2m d square by dx square plus half kx square into psi x is equal to energy into psi x. Or simply, this equation can be rearranged like this: d square psi by dx square plus 2m by s cross square into e minus half kx square into psi x is equal to 0. It should be noted that the potential of energy of the system is equal to half kx square that we previously derived from the Hooke's law. Vx is equal to half kx square, that is the Hooke's law potential energy. So, this is the Schrodinger wave equation of the one-dimensional harmonic oscillator, and we have to solve this Schrodinger equation to get to the final expression for energy as well as wave function of the present system. Now, it is convenient to use the mass rather than reduced mass of the SHO for reducing the complexity associated with the solving of the Schrodinger wave equation. We are still using m as the mass of the particle instead of mu, even though it is more correct. Also, the force constant k of the oscillator is given by k is equal to m omega square, where omega is a term that represents angular frequency. And angular frequency omega is related to vibrational frequency by the relation omega is equal to 2 pi nu. Thus, the above we already learned one form of the Schrodinger wave equation that can be modified by substituting in place of half k square or potential energy to get the modified relation, that is d square psi by dx square plus 2m by s cross square into e minus half m omega square s square psi is equal to 0. So, this is the another form of Schrodinger wave equation which is more convenient and we can solve it more easily. Now, defining a new variable psi as a new parameter lambda as psi is equal to m omega by s cross the whole raised to 1 by 2, and the new parameter lambda is equal to 2e divided by s cross omega. Kindly note the fact that the function psi and lambda are incorporated. The parameter lambda and the variable psi are incorporated in the Schrodinger wave equation in order to reduce the complexity in solving that equation. Thus, the Schrodinger wave equation for the one-dimensional simple harmonic oscillator is given by d square psi by d psi square. Note the change. In the previous equation, we have d square psi by dx square, and that x is now replaced with the psi, and psi is given by m omega by s cross the whole raised to 1 by 2. So we are getting the modified form of the Schrodinger wave equation of the present system as d square psi by d square psi by d psi square plus lambda minus psi square into psi is equal to 0. This term is pronounced as psi, and this term is pronounced as psi. So this is wave function psi, and this term should be read as psi. So the Schrodinger equation for the present system is d square psi by d psi square plus lambda minus psi square into psi equal to 0. This is the ultimate Schrodinger wave equation for a diatomic simple harmonic oscillator. Now, we are moving on to the solution of the Schrodinger wave equation of the problem. We can find out the solution of the Schrodinger wave equation by putting some conditions. First of all, we are finding out the solution of the Schrodinger wave equation, that is notated as equation number 1, and this equation is notated as 1. This equation is d square psi by d psi square plus lambda minus psi square into psi is equal to 0. This is marked as equation number 1. And we are now finding out the solution of equation 1 when psi tends to infinity. When psi tends to infinity, that is when psi is large, equation 1 will be changed to d square psi by d psi square minus psi square psi is equal to 0. And for that situation, there will be an exact solution. The exact solution is psi x equal to e raised to minus psi square by 2 h psi, where h psi is a new function of psi, and h psi later we can consider it as the Hermite polynomial form. Moving on to further solutions, or to get the complete solution, substitute the value of the previously learned psi x in equation number 2 to get the solution. To get the equation, d square h psi divided by d psi square minus 2 psi dh psi divided by d psi plus lambda minus 1 into h psi is equal to 0. Remember the fact that we changed the original Schrodinger wave equation of 1D simple harmonic oscillator into a new form. This new form of the Schrodinger wave equation is known as the Hermite equation. The Hermite equation. Hermite equation, we do this modification because the Hermite equations have direct solutions, and that solution appear in the form of a set of polynomials that are called Hermite polynomials. So to get the solution of the Schrodinger wave equation of 1D harmonic oscillator, we first modified that Schrodinger wave equation into one form of the Hermite equation, and this is that Hermite equation. H psi can be represented as a series of solutions as h psi is equal to n is equal to 0 to infinity, an psi raised to n. This is an important relation. Substituting the value of equation 5 in equation 4, we get a result that is summation k is equal to 0 to k is equal to infinity, k plus 1 into k plus 2, ak plus 2, minus 2k plus 1 minus lambda, ak psi raised to k is equal to 0. This is obtained as a result of substitution of equation 5, which is a summation term in equation 4. So we get the result sum in from k is equal to 0 to infinity, k plus 1 into k plus 2 ak 2 minus 2k plus 1 minus lambda ak into psi raised to k is equal to 0. From this we have to get a new relation that we will discuss soon, that is called the recursion formula or recursion relation. So this equation 6 is very, very important. Now we have k is equal to 0 to k is equal to infinity, k plus 1 into k plus 2 ak plus 2 minus 2k plus 1 minus lambda ak into f psi raised to k is equal to 0. And in this expression, in order that this equation to be valid, for this equation to be valid, the coefficient of each power of psi must vanish separately. That is, the coefficient of each power of psi must vanish. That is, k plus 1 into k plus 2 ak plus 2 minus 2k plus 1 minus lambda ak can be taken as 0. When the coefficient psi raised to k is equated to 0, we obtain a relation, a mathematical relation called the recursion relation. So in order to get the recursion relation, we have to equate the coefficient of psi raised to k, that is the term represented inside the bracket, to be 0. From that on rearrangement, we will get a new relation. That new relation is called the recursion relation. We will get the recursion relation by putting k plus 1 into k plus 2, ak plus 2 minus 2k plus 1 minus lambda ak is equal to 0 like this. That is, we have to put k plus 1 into k plus 2, ak plus 2 minus 2k plus 1 minus lambda ak is equal to 0, or k plus 1 into k plus 2 ak plus 2 equal to 2k plus 1 2k plus 1 2k plus 1 minus lambda ak. Therefore, 2k plus 1 minus lambda divided by k plus 1 into k plus 2, k plus 1 into k plus 2. This quantity divided by this quantity, that is equal to this quantity divided by this quantity equal to a k plus 2 divided by ak. This mathematical relation is known as the recursion relation, or by rearranging this, we will get ak plus 2 equal to ak on cross multiplication gives 2k plus 1 minus lambda divided by k plus 1 into k plus 2 multiplied with the ak. This is the simplest form of the recursion relation. This mathematical relation is called the recursion relation. Now, the recursion relation allows the calculation of all even coefficients in terms of A0 and odd coefficients in terms of A1. Thus, we have two independent solutions of equation 5. H even psi is equal to A0 plus A2 psi square plus A4 psi raised to 4. H0 equal to psi into A1, A3 psi square, A3 psi raised to 4, etc. Thus, we are getting two functions called even functions and odd functions. The even functions and odd functions can be obtained from equation 5 like this. We have this equation, that is equation 5. H psi is equal to n0 summation n is equal to 0 to infinity an psi raised to n. Now we can expand this relation. H psi is equal to, now we can put n is equal to 0, 1, 2, 3, etc. A0 psi raised to 0 plus A1 psi raised to 1 plus A2 psi raised to 2 plus A3 psi raised to 3 plus A4 psi raised to 4 plus A5 psi raised to 5 plus etc. And in this term, if you are collecting the odd terms, odd coefficients together, we get H0 psi, and that is marked as the odd function. Thus, HO psi can be marked as A1 psi raised to 1 plus A3 psi raised to 3 plus A5 psi raised to 5 plus etc. This is termed as odd function, and H even function is obtained by picking the even coefficients. That is, H psi is equal to A0 into psi raised to 0, that is taken as A0 plus A2 psi square plus A4 psi raised to 4 plus A6 psi raised to 6 plus etc. Thus, we got two functions, that is H even and H odd, that is H e psi and H o psi. E represents even and O represents the odd function. Now, the Hermite polynomials. We shall now determine the energy eigenfunctions of the simple harmonic oscillator. Put the parameter lambda is equal to 2n plus 1 in the Hermite equation that we already obtained. We have the Hermite equation, and in the Hermite equation, we have to make a simple substitution, that is lambda is equal to 2n plus 1. So, on substituting lambda is equal to 2n plus 1, we get the relation d square hn psi divided by d psi square minus 2 psi d hn psi divided by d psi plus 2n hn psi is equal to 0. The solutions of this equation, this is another form of the Hermite equation. This is obtained by putting the previous Hermite equation or making a change in the previous Hermite equation by replacing lambda with 2n plus 1. This new equation has a solution, and the solutions are known as the Hermite polynomials. Hermite polynomial of degree n can be defined mathematically. Hn psi is the Hermite polynomial, that is equal to minus 1 raised to n e raised to psi square dou raised to n e raised to minus psi square divided by dou psi raised to n. This is the mathematical expression for Hermite polynomial. Hermite polynomials are solutions of equation 8, that is Hermite equation. So, equation 8 have a solution known as Hermite polynomial. The Hermite polynomial of degree n is given by this equation. We can put different values for n such that we will get few Hermite polynomials. For example, if we are putting the value of the degree n is equal to 0, we will get h0 psi. h0 psi is theoretically, on solving that, by putting the value of n is equal to 0, we can prove that h on psi is equal to 1, h2 psi is equal to 4 psi square minus 2, h0 psi is equal to 1, h2 psi is equal to 4 psi square minus 2. If we are putting n is equal to 1, we will get h on psi, that is equal to 2 psi. And if we are putting the degree n is equal to 3, we get the value of h3 psi as 8 psi cube minus 12 psi. So, these are the values of first few Hermite polynomials. Now, moving on to wave functions of 1D simple harmonic oscillator. The unnormalized wave function of 1D simple harmonic oscillator can be represented by incorporating the Hermite polynomial like this. Psi n psi is equal to nn, hn psi e raised to minus psi square by 2. Here we can put the value of hn psi, that is Hermite polynomial, that previously we learned. We can substitute the value of hn psi and we can make proper simplification. On normalization, we will get to the normalization constant nn also. Thus, on normalization, we will get to the final wave function as psi n psi is equal to m omega by s cross pi the whole raised to 1 by 2 into 1 by 2 raised to n factorial into n factorial the whole raised to 1 by 2 into hn psi into e raised to minus psi square by 2. Now, we are moving on to the energy of one-dimensional simple harmonic oscillator. On solving the Schrodinger wave equation for one-dimensional simple harmonic oscillator, we get expression for energy as En is equal to n plus half h nu, where n is equal to 1, 2, 3, etc. And n is equal to 0, we get energy is equal to half h nu. This energy, when a value quantum number is equal to 0, is termed as the 0-point energy. It is the lowest possible energy that a quantum mechanical physical system may have. Now, these are various energy values. We can put n is equal to 0 to get half h nu, n is equal to 1, 3 by 2 h nu, so on. So, from this, it is clear that the energy levels are equispaced and the spacing equal to s nu. This about the graphical representation of energy as well as wave function and probability associated with the 1D simple harmonic oscillator. This is the representation of psi 0 and psi 0 square, and the energy levels, as I mentioned, it is equispaced. Thus, we have discussed the one-dimensional simple harmonic oscillator, the Schrodinger wave equation, its solution, and the Hermite polynomials and associated parameters. That all about the discussion. Thank you.